I'm really excited about this video. Okay, so I've been arguing with everyone for a really long time now whether or not, alpha, beta interact with gamma X-ray and how and why they do in not only our magnetospheric bands, but the magnetospheric bands of the sun and how they intertwine with each other. And in other words, I've been trying to get everyone around me to understand how linear accelerators work. My wife specifically, and a bunch of my friends, people close to me, I want them to truly understand why this technology that is over in Europe curing cancer is such a big deal, and why our studying of space is actually what brought us this technology. So this video is perfect because it's going to not only force people to understand about linear technology, which will help people start to understand what LIGO is and how and why that system works, and what it has to do with CERN and GSI and various places like that. It's a great step towards everybody getting a greater understanding of the basic of particle physics that should be relatively understood and known by all the common people. Basic, anyone in school in like the 7th grade should get a rundown of this now. So the differences in power and the differences in radiant energies are what they're going to describe and explain here. The reason why this is such an important video is GSI has talked very specifically about carbon-14 and the alpha particle that they use in their accelerators, and what it was they used in the test to show when NASA asked them, please, let us know exactly what it would be like for a particle, one of the galactic, cosmic background particles, or something, really heavy, direct from our star, some cosmic, ray from our star. And so they're like, all right, we'll do our best, give us the projected data, something you have an idea of what it's like. And they're like, well, we believe that Mars is like, and we think that, so it might be a relative like that. So base it off of that, and then, go from there with, just the relative physics that we have the mathematics for. So they did their best, they created the particle, and they shot it into a cell. And what happened is, well, check it out.
Image that you see, what you see here, this one is a human cell. This is a human nucleus, it's 10 microns approximately, and these two lines that you see here are two iron ions that you don't find in space, I'm sorry, that you find in space but not on Earth, except in Darmstadt and GSI where we have it, going through the cell,
layers of the atmosphere.
Damage to the DNA.
So, obviously, the cell decayed, and there was nothing, you saw the time lapse, it's 3 seconds, and immediately it's penetrated. Nucleus is, the DNA is dead, it's not going to produce any usable RNA, the cell is toast, it's going to create cancer as problems to the host. So, that's what happens, that's what we knew would happen, and that particle right there, that's a carbon-14, it's an alpha particle, and it is about 200 sieverts. Now, they're going to talk about this in the end of the video, but just keep that in mind. That is a typical particle for deep space.
The term radiation is thrown around a lot. Like, you may have heard that your cell phone gives off radiation, or maybe you just want to understand whether those x-rays your doc ordered are dangerous. But we can't have a really meaningful conversation about the relative dangers of radiation exposure without being clear about how much radiation we're talking about. And unfortunately, thanks to some accidents of history, the units we use to measure radiation and radiation exposure are kind of a mess. But there's only two you really need to understand: the gray and the sievert. To rewind a little, let's start with that term radiation. In physics, it refers to the energy carried by particles or waves. So technically, everything that reflects or emits light is giving off radiation. But
so, first I want to talk about the fact that everyone uses that as their scapegoat. Every single conversation I've ever carried on with anybody who thinks we've gone to the moon and that, radiation's no big deal, you just gotta go really fast to the Van Allen bells. All of this crap, it's awesome because this is their first fallback. Oh, you don't know what the fuck you're talking about, man. Radiation's everywhere. Don't you know that banana is radiant? Don't you know that all of these things are just, radiation all around us, and it's not a big deal. Just calm down. You need microwave as radiation. This is why they say that, and this is why it doesn't matter that, yes, everything has radiation. There are various levels of radiation. what they're not going to touch on here is the atmospheric levels that define those different types of radiation. Why we don't have the type of radiation where the International Space Station is, 230 miles up. However, the International Space Station doesn't have the radiation that's 1,000 miles up. And the International Space Station's radiation and the 1,000-mile radiation points, completely different, and a huge difference. Not way, like 20 times what the International Space Station to our radiation count is. So there's layers, and then of course there's anything past the first band right there, and then there's of course outside of the band where there's more than the 1% that the 1% of the 1% the International Space Station gets, and then the 100% that's outside of the bow shock. Look at every single model of the magnetosphere we've ever created, and you'll see 99% of the particles going around the invisible shielding of Earth. And that's what we need on Apollo to leave the shield of Earth. This shield like Earth. So, radiation levels, yes, but the layers of Earth protect us from the different layers of levels that radiation can be found. So, they're not going to talk about anything outside of radiation exposure on Earth, within the troposphere. Maybe the stratosphere, but I don't see them talk about any of the plane exposures, the people that, that are in the stratosphere, fly of these, heavy flight or long flights all the time. They have to do extra radiation exposure because of the REM count they're exposed to, which of course we don't use the REM count anymore. They'll touch on this later. I'm so glad they finally get around to saying that it's outdated. Like the Van Allen belt studies, it's no longer considered the Van Allen belts. It's our magnetosphere, and it has dozens of bands with dozens of names, and it's not just two. And it does more than just hold stuff inside of it. It doesn't make it, it's out there. Some gets trapped inside and bounces around. So,
generally, when people talk about harmful radiation exposure, they mean ionizing radiation. That means
again, remember GSI? This is ionizing radiation. Now, if you watch the entirety of that lecture, you'll find that Marco Durante very clearly states that in order to leave Earth's active shielding, you need to have active shielding. So, there's that. Or if you don't need active shielding, you need to be like the Hulk. And that's why he holds up the little figures of, the Marvel comics and says, you gotta be like these guys if you want to, be exposed to the radiation that's ionizing. So, because it'll break down your body and destroy it, your body has to produce the same amount of it to counter it so that it can be within the environment that it's made of. So, if you want to be like stardust, you have to be of stardust. And, well, that's ionizing particles. We're not ionizing. That's what makes the difference between the mesosphere and the stratosphere, is ionizing radiation and the molecular structures that are allowed to be within the stratosphere but not within the mesosphere because of that ionizing radiation. So, to be within the environment, you must be able to be of the environment. A little bit above it we can go because with certain passive shielding, and that's where a lot of other people go, oh, see, we use shielding all the time. Don't you know that the International Space Station has tinfoil, and it uses lead and water, and the coolant systems, of course, is what they'll go off on, because it's not just water, obviously. Although the new Orion capsule they show with, I have it on my channel, they show that he's just piling stuff around them to survive little, gamma ray bursts and any solar energetic particle mass releases from the star, and so they'll be all right with that. But I digress. Anyways.
With enough energy to rip electrons off of atoms or ionize them. This is the radiation we care about being exposed to because it carries enough energy to break chemical bonds and cause mutations to DNA that increase your risk of cancer. And to get this one
again, exactly what GSI showed, proving everybody knows about this. We have to slowly release the information to you guys because we can't just come out and be like, hey, we didn't go to the moon. The sun is actually ionizing us at a rate we can't figure out. It's causing this climate to change dramatically, and we can't really stop it. We're scapegoating with it. It's all your fault, but it's not all your fault. It's just you're definitely not, stopping it or learning about what's causing it. And so with all of this, we can't just drop it on you because, well, that'll cause riots and panic, and the nationalist pride will drop, and everybody will be like, well, what's the point? And we've all seen human beings hit depression, and this would be a global depression. So of course you're not going to just drop all this immediately. However, there's more to NASA, SciShow, VintageSpace.com, every single publication constantly talking about why we can't be up there and why we have to stop at a certain place up there but can't actually go all the way up there, and why we're not out anywhere. We're just 230 miles up, where we can start to manage some of the ionizing radiation. But really, we need Marco Durante to tell us why, so we can send Francis S. Collins, the lead geneticist of the world, the guy who broke the genome and can tell us about DNA, to work with people like Kate Rubins on the International Space Station, the first non-military biologist to ever go up there. All of these people to try to figure out how we can go 1,000 miles up, a little bit further. And until then, Russia made a robot. Did you see? Just last week they sent that up in the Soyuz. I mean, it needed help docking, but... there's robots now, so they're going to send those robots about 1,000, miles up because, well, ionizing radiation. We can only handle so much of it, and for only so much time. About a year, we're all right. Any more than that, weird anomalies start to occur. Not so much genetic decay as it is structural decay, various things like gravity we're still blaming on, but the reason we don't push above all of that is just straight up ionizing radiation. The levels that get worse, they're going to talk about.
Out of the way real quick, cell phones don't send signals using ionizing radiation.
No.
They use radio waves, which don't have enough energy to damage cells.
However, 5G, gamma and X-ray communications, they do use some ionizing radiation. They're going to have to come out with that eventually, but this is more duck and cover. It's like the vaping and everything else having to do with lithium-ion cell phones, because if cell phones don't have, they don't produce the waves that our communication is what he's talking about, and they don't produce gamma X-ray, waves in the ways that the 5G systems are now starting to communicate for the governments, and those are actually what we need to start worrying about, is whether or not every individual has that, and there's mass stations, and then the field that will create around. Obviously, that might cause people to be like within an environment that's kind of like having an X-ray all the time. Mild dose, like 0.05 millisieverts, tiny. However, if you acknowledge the simplicity of the name of the fucking tool, again, this is something we're just not acknowledging, lithium ion. It is an ionization process. What do you think the lithium battery is, and what do you think the process that causes electricity to occur is doing? Why is it not exposable to oxygen and various other elements? Why does it have to be encased a certain way? Why is it that they only use polymers to encase these things? There's a reason for all of this, and it's because it's fucking ionizing radiation. So when you hold your phone, you're getting ionizing radiation. Just nothing that's really worth concerning yourself. It's not going to change your genetic structure. It might if you put it on a really sensitive spot and you leave it there forever. I mean, girls that put it in their fucking bra or tuck it right here and shit, yeah, you're going to get boob cancer or some ovarian cancer. You're fucking asking for it. Lithium ion, ionizing radiation. However, the communication systems used to send signals that are the phones calling, texting, downloading and uploading information like videos, YouTubing, and shit like that. That is not ionizing radiation. So that's what he means. It's a nice little bullshit, a way for them to, radiation's everywhere. It's just, don't go above 1,000 miles or you'll see what happens Marco Durante showed. So it's scapegoating. It's propaganda. It's stepping lightly around the truth while still pretty much stating it. The finest thing NASA does.
Ionizing radiation we worry about most comes from nuclear decays. That's when an atom breaks apart into smaller chunks, releasing other particles in the process.
Cosmic
and
background
how easily
radiation.
These particles can ionize is in part
Solar
determined
energetic
by
particles.
their energy. So that's where we get to our first radiation units. Particle energy is usually given in units called electronvolts, or EVs, and a typical radioactive particle may have an energy of about 1 megaelectronvolt, or MeV. That's 1 million EVs. And while that might sound like a lot, it's nothing compared to our everyday standard unit of energy, the joule. The energy needed to lift 100 grams up by 1 meter, which has 6 trillion MeVs in it. So I just want to point out really quick
that's a beautiful way to try to create a comparison. However, creating a comparison of how much energy it creates to lift mass and how much energy it is comparatively from a particle to a particle is completely different. And why wouldn't they have done, that's what they should have done as their comparison. So, would you like to know the comparison? The single particle is to the single particle the same. Now, obviously, depending on the particle's mass, it will be different. The volts it carries will be different. Obviously, nitrogen has a greater capability than hydrogen. However, simple things like, depending on your mass's structure, play into how much you're putting out. So if we were to take one particle to one particle, it's just 1 to 1 there. It's not 1 to how much it takes for all of this energy in comparative, you know, it's not the same, and it's a nonsensical study. It would be one particle to one particle. Now they're going to go off on how many particles, you know, we don't even know how many, you know, you might have, because that's true, because each individual person has a variable of what particles are made up of. So you can't actually say this person has this much electricity per cubic centimeter squared. That's impossible. However, we can give a roundabouts of you have 7 times 10 to the 24 particles per cubic meter squared. We'll just assume that it's a hydrogen base. That way it can start off as 1 to 1, and everybody can do a basic mathematics equation to how much energy a single cubic meter squared, your human body, is made of. And so that would be an adequate and apt comparison. They're not doing that. There's a reason for it. It's like them talking about everything's radiant and, you know, oh, you know, there's levels to it. It's just, you know, not layers to it, or there's no reason why we're exposed to certain amounts or not, why some people are fine and some people aren't when you're encountering certain amounts of radioactive properties. Depends on what you're made of. Some people can take it better than others. Some people, they walk out in the sun and they get sunburnt real quick. Some people don't. There's reasons for this. Our genetic properties have the ability to displace our molecular structures so that we have either a better or worse chance at surviving the greater output of energy that is put on us.
A particle has a tiny amount of energy on a human scale. Of course, radioactive sources don't generally give off 1 particle at a time. So we also have units to describe how many radioactive decays happen in a source per unit of time. 1 becquerel, the standard unit for decay rates, means your source has 1 nuclear decay going on in it per second. Basically, a tiny amount of activity. Your body typically and safely emits several thousand becquerels all the time. There are older units.
Yes, but we all know, oh, okay, so most people know, and if you don't, check out exactly what a kilocal is and exactly how it is that we create energy and what, you know, what calorie burning and how we measure the process of energy to calories is, and how we came up with these so that we can measure how much energy we put on.
To describe decay rates too. The Curie, for example, was based on the decay of radium-226, but it's now defined as 37 billion becquerels. Somewhat related is the Röntgen.
Again, notice that they use this great amount to compare it to this singular point, and so there's almost no applicable comparison except for point to point, and they completely avoid that. So, and then GSI studies show what would actually be if they just let the actual particle that they were just referring to touch a singular one. So that's the particle that hit the massive particles that was that cell, and
which was in fashion for a while and recently popularized by the Chernobyl miniseries on HBO. It focuses on the air instead of the radiation source. Essentially, it quantifies how many electrons are being knocked off per cubic centimeter of air.
Again, why is that? If you watch the documentary about, you know, them building the dome over Chernobyl, and you learn about what they're actually protecting the surrounding environment from, you'll know that it's not the particulates. It's not the alpha and beta particles that are now found in the sediment, in the animals, everywhere that they can measure. If you look at the x-rays of their limbs and their sediment and everything. Like, you'll see these little black specks all over. Those are the things that if you eat that, your body can't get rid of it. That's where you get the, you get your liver cancer, you get your colon cancer. These are the ways that we die. We inhale those little particles, and that's how it gets us. However, what they're talking about here is the same reason why they're building a giant cement dome over Chernobyl, why everyone's starting to be interested in Chernobyl, why we're creating X-ray gamma telescopes, and Russia's shooting all that into space to look at the moon and the cosmic background and our star in greater detail, because we're recognizing that X-ray and gamma rays, these serious wavelengths that we didn't give enough credit to or understanding to, they're playing a huge role in everything having to do with molecular compounds and the structure of everything that we have within our environment. So the radiation that Chernobyl's putting off is gamma X-rays, and they don't arc, so you have to go with the curvature of the Earth. That's why they're building it away from it, just below the arc of the gamma X-rays, and why they'll slide it over once the structure is complete. It's actually an amazing feat of mathematical engineering how they've created the ability to avoid gamma exposure while creating it on site. If you haven't seen the documentary, check out that Chernobyl building the giant tomb, cement, whatever they're calling it, sarcophagus for the elephant's foot. Check it out, it's cool. So.
And if you're standing next to something emitting 1 curie of radiation, or in a room where a whole lot of electrons are being knocked off of air molecules, it's probably not great for you. But from a medical...
Probably not great for you. Yeah, we just saw it. Marco Durante of GSI shows what happens when you are exposed to that chemical. Also, look up Anatoly Bogowski. He was exposed to these raw particles. Anything that is driven through X-ray, gamma, any of these linear accelerators that use light and to push light, or use light to push mass. These particle accelerators also show, just like GSI, what would happen to the tissue. And he got a proton right through his head, and it was like being shot by a bullet. However, it was just a single element. It was one proton. But the fact that that proton at 76 GeV, which of course they're not talking about that being the weight of all of the particles that they're measuring, because they're talking about the elements that they're measuring here on the troposphere, which of course are non-ionized. However, the protons within those accelerators, these type of things are heavy ionized particles. So, just like out in space, where they start off at 10 GeV from the chromosphere, and there are UCLA and Princeton lectures. A girl named Annika does a great lecture, I have it on my channel, talking about the GeV sun and how it is that the magnetispheric bands of the sun accelerate, just like our particle accelerators, up to 255 GeV from a base of 10 GeV, and all the way up to, we just discovered last week, galactic background cosmic particles that are upwards of 100 TeV. So there are a great amount of heavier and faster moving particles that we know what would have happened to us if we were exposed to them. And it's not just bad things. He survived, like some people survived getting shot in the face. He survived, sure. However, when he survived, his face got paralyzed. It cauterized the wound instantly because it was so hot and so heavy, and went right through him and left a scar on both sides. And to top it all off, they had to worry about radiation from it just passing through, from whatever it touched burning on its way through. So if you were to get that into you and it were to stop within you, if you were to go through enough layers to where it just embedded and stopped into you, you're gonna get cancer and die no matter what. If it goes through you, you'll survive though. So that's what we learned about that study. However, it will go right through you. So anything greater than about 10 GeV just goes through us like a bullet. So if we were to leave, any of the Earth's magnetosphere, the entirety of the bow shock, passing the magnetosheath and everything, leaving the plasmasphere, all of the bands from there to there and in between, all of them, we would just disintegrate. First, it takes a long time to get there, 25,000 miles, don't kid yourself. Apollo took days, like the Soyuz took days just to get 230 miles. We've now figured out orbital mechanics to a science, and now it takes upwards of between 4 hours and 4 days, depending on exactly where we're syncing up to and how easy it is to get right there. But bottom line, going up, it takes a long time. Voyager's just hitting the bow shock. just leaving. That's why we're losing communications with it. Spitzer and Kepler are next. They spin them around just like the Kepler and take a picture. Right before we lose contact with it, when it starts to hit the plasmasphere, it's done. So we have plenty of reasons and plenty of examples, all scientific studies showing why and what will happen when the particle hits us. And it's not just, oh, you know, some bad things could happen. It is instant death or instant cancer.
And these two lines that you see here are two iron ions.
And most of these cancers you can't fight off. Like when Apollo 13 went 1,000 miles up, the oxygen tanks ionized from this ionization because it's biradical. It's really easy to expand. And so with all these free radical electrons ready to find their quickest way out through the opening nipple part where it allowed it in and out, not only did that happen, but those men, 2 out of 3 of them, died of cancer. The same cancer Marco Durante showed you'll get if you actually go that high up. The same cancer that they just talked about, you know, maybe it would be a bad thing, because even if you come back to Earth immediately and start getting all the cancer treatments constantly for the rest of your life, they did not want those men to die of cancer. Like as soon as Jack died of cancer, they're like, oh shit, don't let anyone else go. And then of course Fred died of cancer, and so, well, Princeton says that the particle mass, as they're going to talk about here, is one particle for every 3 of ours per cubic centimeter squared, or per cubic meter squared. So, there's plenty of them out there. It's not an empty place. Space is hot, space is full. It's a sea of plasma, and we are a ball in the bottom of the ocean, protected by an invisible barrier.
Perspective, it's not enough to know how many particles of radiation are in a room or being emitted by something. You need to know exactly.
Again, yes, I just stated there is. Princeton. It's the study that I have on my wall or on my channel. Take a look at it. It explains very clearly the amount and the properties within the plasmasphere all the way to the magnetosheath, and then the variables that could be an occurrence, working with Annika's presentation on the chromosphere to our bow shock and the magnetic electromagnetic properties between those points, and what happens and why the particles have such an interesting path and sometimes a reversible path between those points, and how they're also built up and have a heavier turbulent plasmic state like our magnetosheath, and how all of them are in a great number of mass, a definable mass. Watch those, they're actually worth watching.
Exactly how much radiation your body is absorbing. This is called the absorbed dose. The standard unit for the absorbed radiation dose is the gray. A dose of 1 gray means that 1 kilogram of matter has absorbed 1 joule of radiation energy. For instance, a CT scan in a hospital might expose you to 7 milligrays, or 7,000ths of a gray. Some people still use the rad, a historical unit now equivalent to 0.01 gray. But whether you're talking rads or grays, there's an additional complication. Some types of ionizing radiation do more damage to the body than others. So the same amount of grays can do different amounts of damage depending on the type of ionizing radiation.
I have been screaming this for so many years and everyone has disregarded it, and now it's going to be common knowledge. So first I'm like, grrr, you fuckers, see, I told you so. But at the same time I'm like, awesome, see, I told you so. And now we all know.
Types of ionizing radiation, but the 3 main ones are called alpha, beta, and gamma. Each refers to a different type of particle ejected
Gamma, X-ray are the same.
Alpha particles are the heaviest, slowest, and most easily stopped, while gamma particles are the lightest, fastest, and hardest to contain.
Take that shit in right there. Again, how does a linear accelerator work? How do we use the things that we have as tools on the Earth to study the properties that we're discussing here? Very simply put, we have the ability to understand that light can move mass. And in moving mass, it can move mass we want it to move to a variable point in mass. My wife now is actually having to work with cancer patients in the medical field that she's in, and she has to deal with linear accelerators that were just now brought into the Good Samaritan hospitals. So, where we have to deal with radiation treatment, now we have to understand what it is we're exposed to. So with all of the old techniques that they used to have, you would have to, with chemo, stuff like that, you would have to worry about there being an exposure that the person could give someone else after they've had treatment. Well, I've tried to tell her for years that with linear accelerators, it's not like that. The amazing thing about this technology is they're using electricity, they're using light, electrons, to move mass out of the way, to take mass and place it direct point to specific mass that we don't want there anymore. We want ionized, we want burnt. And so, that, of course, that electricity will burn things out of the way, but I mean, it's creating active shielding in a way that we're just starting to acknowledge and understand to move mass through. So if we want to talk about faster than light travel and ion drives and the electromagnetic shielding that we need that potentially could be derivative from an isotope, then, well, we're in the process of making all of this, and through admitting these things right here and getting everyone like you guys to acknowledge this, all of a sudden it's going to just explode. The technology, more people will be thinking about it, and we'll be able to understand that, oh, these linear accelerators are causing mass to be moved by light, and moving mass to move with light to move mass into mass, and then stop entirely, and there be nothing, and everything go back to how it was. Because we're starting to understand that's what electromagnetic reconnection points are within our neutral point, within the plasmasphere, within the magnetosheath, within all the variable points of the surrounding active shielding that we have protecting our mass. How does the mass from outside ionize us? Oh, this is how, and so we created the machines, and bottom line, this is one step closer to everybody being able to understand why it is we are furthering our technology in the medical field through space exploration, and why space is so important.
And that's what finally brings us to the sievert. It modifies the gray to account for the different health risks associated with these particles. To get sieverts, you multiply grays by a number specific to each type of radiation. Most of the time, like for beta and gamma particles, the number you multiply by is just 1.
But with all find the space, I'm sorry, but you find the space.
Alpha particles, you multiply by 20, because alpha particles pack a real punch. And that 20 number isn't arbitrary. It's chosen based on the latest, constantly updated research into the effects of radiation on human health. In that
Marco Durante is the one who set the standard for it. He is the leading physicist for all particle physics research for the European divisions, and the European divisions are the ones who have created these studies. So GSI is the one creating these studies. The end.
The sievert is a unit for human convenience. It takes the gray, which measures something exact and physical, and modifies it to tell humans how dangerous a type of radiation exposure might be when it interacts with our bodies. You also may have heard people talk about REMs when discussing exposure. It's the same idea, though an outdated version. REMs is short for
Outdated.
Röntgen equivalents in man. 1 rem is now defined to be 0.01 sieverts. But really, the sievert and the gray are the only units you need to remember to understand the overall impact of radiation exposure and make...
And again, remember, 200 sieverts exposure is basic exposure to the mild galactic cosmic background rays that we are exposed to, and the solar engendered particles that the sun puts out. These, unshielded by the Earth's magnetosphere, this is just the basic consistent. And this is all the best that GSI could come up with off variable data, all projected data that pretty much we created through experiments in the Atacama deserts and in the mountains of Chile. And so with the study in the Chilean mountains, we came up with the projected data and gave it to them, and they went, okay, well, here's some other projected data. And bottom line, that's why the Parker probe was made. And the Parker probe was sent out because it's not going to be projected data. It is going to actually go in above the exosphere. We hope above the exosphere. It'll be one of the first probes to do it, besides Themis and the MMS missions that have actually touched the plasmasphere. And it's going to hopefully touch that and get one of the raw particles, an actual example of the raw particles. Now the Parker probe is nothing more than the Genesis probe redone. We actually tried this in the early 2000s. We tried to send one to the plasmasphere. However, solar energetic particles, they destroyed its capability to function, and the signal was lost, and the parachutes fritzed, and nothing worked. And so on its orbit, when it slammed back into Earth, and it was supposed to open the parachutes, it just slammed right into Earth and blew up into a bunch of pieces, and all of the cells were exposed, and we couldn't actually study the particles that the plates hit when they were within the plasmasphere. And we lost contact with it, so we didn't know exactly where it went for a while, and when it came back, it was fritzed, and it was a disastrous mission. So the Parker probe is them hoping to redo that mission correctly without the failures of last time happening. And we're hoping now, with understanding ionization a little bit better, especially with the new gamma X-ray technology that just came out, hopefully we're going to be able to get just outside of the exosphere, where the new communication satellites are hopefully doing elliptical patterns in. Why, you know, India and Jerusalem and all of them are on the moon. There's the second stage communication satellites. We're finally in the exosphere. Took us till, you know, the 80s to get, you know, into the middle of the thermosphere, and now we're finally in the 90s and 2000s hitting the exosphere. So hopefully that's going to get, you know, the raw particles, and then we'll have more than just theory, more than just projected data to base all of our ideas off of.
Make informed decisions about how you travel, receive healthcare, and generally live your life. Because the truth is, there are a lot of sources of radiation, including natural ones, and everyone is constantly exposed to some of it. On average...
Again, that's the, oh, radiation's everywhere, disregarding the fact that the radiation everywhere is defined by the atmospheric layers and protection from all of the particles that are the dangerous ones surrounding all of those bands that protect us.
People are exposed to a few millisieverts per year from their everyday life. The amount from medical scans varies depending on the size of the scan and the duration in the machine, from less than 0.01 millisieverts for a quick joint X-ray to about 10 millisieverts for a full abdomen CT.
So, first thing I wanted to point out, look how quickly they just jumped over. Oh, you know, you just got a little bit each year. Of course, you know, on the surface of the Earth, within the lowest level of the troposphere, surrounded by all of this matter that also is kicked when dust kicks up, there's a protective layer, any of the clouds, protective layers. These are all ways that not only the troposphere but the stratosphere keep you protected from ionizing radiation. So when we talk about the gamma and X-ray exposure, things that would cause alpha and beta particles to travel at a faster speed of rate or become heavier, any of these particular things that cause ionization to a particular particle or cell, anything that causes molecular breakdown, as they're talking about here, this would be found more and more as you go up. Why it is that the International Space Station is only 230 miles up.
These raise your lifetime risk of cancer by 1 in a few million to 1 in 2,000 respectively. And to put all that in perspective, the allowed limit for the average nuclear industry employee is 20 millisieverts per year. The point is, while radiation exposure can be bad, it's also something that happens to us every day. And once you...
When you're confined to the troposphere on Earth's atmosphere, safely surrounded by the stratosphere, the mesosphere, the thermosphere, the exosphere, the plasmasphere, the 7 different neutral point bands that have polar cusps that allow only 1% of the 1% that's in the magnetosheath to actually filter into us, that is all only 1% of what is actually the dangerous ionizing radiation that is within the bow shock, that is 100% of outside outer in deep space. Now we are in outer space, 230 miles up, within very, very, very few of these high energetic particles. Very few, because we're safely within all of those bands I just discussed. However, when you're 6,213 miles up, traveling outside of the exosphere into the plasmasphere, you're talking Princeton's numbers, and those aren't rare anymore. That's 1 to 3. That's not 1 in 100 some odd million that they're talking about by the International Space Station. So, and that's definitely not what we're talking about on the troposphere here. So we are totally safe because we have all of the various layers of atmosphere and magnetospheric bands protecting us. The projected data came from the Mars research. Obviously, Chilean mountains, where you can find upwards of approximately 200 REMs in certain points depending on the time of year. Why we can't live there, why it's inhabitable, why there are various studies, and why they didn't have the Mars, group from France, from ESA, they didn't have them down in the Chilean mountains, they had them in Hawaii. Because you don't want to actually do it where we're trying to pretend Mars is, because people might die. Mars is deadly. Mars is almost as deadly as deep space. Definitely not as deadly though. Because, well, as they keep trying to say, maybe there's some slight atmosphere, maybe there's some protective layers still around it, maybe it's not as bad as deep space. But everyone like Marco Durante, if you haven't noticed in all of his presentations, says that, yeah, maybe on Mars, sure, but in transit, here's the particles you have to actually deal with. And they're greater, so there you go.
Understand the lingo used to describe radiation, that fact doesn't seem so scary. Thanks for watching this episode of SciShow, and a special thank you to our channel members. You see, we're only able to make free educational science content like this episode because of the support of our viewers. You can become a channel member.
Okay. Did you notice the last episode they want you to sign up for all these other pieces and all this fucking... Yeah. No, they're only able to do it because they make a shit ton of money telling you guys what you need to know. You think Betsy DeVos only does it for the love of education? Are you people this fucking stupid? Get the fuck out of here. So that's what's going on with radiation. I'm glad that you're all, able to understand what I've been fucking screaming, I'm sorry, because I'm an astrophysicist and I like to point out the relative fact that, every astrophysicist, the number one thing they're telling everybody in the world and why no one wants to hear it is the sky is falling. No, for real. The sky is falling. At all times, in light and matter, it's crushing down on us. You want to see some models? It's neat. The sky is falling. So, told you so. It's only getting better every day. We're not going to the moon. Flat earthers are in charge of NASA, and you have to admit what the fuck we know eventually. Good times.